All right, this is a lesson that I want you guys to be familiar with because every single Calc 1 class in college teaches this, and you will see this in future calculus classes. Possibly in Calc 2, but most likely Calc 3 if you end up taking Calc 3. It is just a technique to find an antiderivative that you don't know yet. The BC students had to know it. I would consider this Calc 1 material that should be in the AB, on the AB Calc test, but it used to be on it, it's not on it anymore. It is kind of also considered, instead of antiderivatives by parts, that's one way we call it. You call it UDV integration, UDV. Okay, I'm going to show you a quick example of why we need UDV. Let's say we want to take the antiderivative of x sine x. And we'll come back to this one. Well, we know that this antiderivative is not 1/2 x squared negative cos x. Right? Because if I thought this was the antiderivative, the derivative of this would have to be x sine x. But if I take the derivative of this, I have to use the product rule. Definitely not going to get x sine x. So this is wrong. So just looking at it doesn't work. The next thing I would try to do is probably use u substitution, right? And I'd probably set u equal to what? Maybe sine, maybe x. What do we think? We could try either. Well, du is equal to just dx, or du is equal to cos x. Let's see. I would either have the integral of u sine u du. That doesn't help me. It's the same thing as this. Or we would have x times u times 1 over cos x dx. Or du. Does that help us? No, that doesn't help us either. So u substitution doesn't work. You can't take the antiderivative by looking at this. However, there is a technique to find this antiderivative, and we will use antiderivatives by parts, integration by parts, or UDV. Where does it come from? It comes from the derivative of UV. I'll walk you through where we're going to get this kind of formula to help us take antiderivatives of tough-looking but specific-looking expressions. So derivative with respect to x of uv is the derivative of u, so du dx times v, plus the derivative of v dv dx times u. And what I'm going to do is take the antiderivative of all of these things. I'll take the antiderivative with respect to x. Well, the antiderivative of the derivative is just going to be what I start with. Over here, I'm just going to write out these integrals, but I notice that these dx's cancel. So this is the antiderivative of v du. This is the antiderivative of u dv. Well, there's that u dv that I kind of talked about up here. I'm going to solve this for this. So that means I can subtract this, or maybe I can just subtract this part and have this just left on the right side. I'll end up just putting it on the left side just so you can see it. We say the antiderivative of u dv is equal to uv minus the antiderivative of v du. Well, this is it. This is where the magic happens. what does this do? This allows us to rewrite any antiderivative as this expression. So whenever we see a product, or we don't even have to have a product, whenever we have a tough antiderivative, I will be able to rewrite it as u times v minus the antiderivative of v du. Now, when we'll actually use this is when this is tough to antiderive. I don't want to just say u, I'm going to say the entire thing. I can't antiderive easily. So no rules, u substitution doesn't work. What you're going to do is you're going to rewrite it as this. And when you rewrite it as this, you end up with this antiderivative of v du. This is going to be an easier antiderivative that you can take by hand. So what we're going to do is we're going to go back to this x sine x. And we're going to use our new rewritten technique, this UDV. And I'm going to write right above it just so you can see. If I have some antiderivative UDV that I don't know how to do, I can rewrite it as u times v minus the antiderivative of v du. Well, what I'm going to do, right underneath this integral, I'm going to have to figure out what is u in this integral and what is dv. I'm going to have to split this into like the two separate pieces. What is u and what is dv? Now, just because it's lined up like this, I'm going to say u is x, and then dv is the rest. Now, u and dv have to include everything. So u is going to be this x, dv will be the sine x and the dx. Okay, so that's my integral u dv. Now, I say that I can rewrite this as uv minus the antiderivative of v du. But I don't know what v is, and I don't know what du is right now. But I actually can find du, and I can find v. How would I be able to find du if u is equal to x? Just the derivative. If u is this, the derivative du would be equal to the derivative of x, which in this case is just dx. We kind of use the u substitution techniques where we have implicit derivatives. We include just the top part, this like du, and the dx. Now to find v, I'd have to take the antiderivative of dv. Antiderivative of sine x is negative cos x. So this was the derivative right over here, and I took the antiderivative here. Well, now that I have this, I can rewrite this antiderivative that I didn't know how to do as this. So it's uv, so u times v, so that's u times v, minus the antiderivative of v du. Well, here's v, here's du. And notice after rewriting this integral, the integral of negative cos x dx, I can find this by hand. I won't say by hand, but I can find it easily. The antiderivative of negative cos x is negative sine x. So turns out the antiderivative of x sine x is negative x cos x minus negative sine x plus c. And this is the same as plus a positive sine x. There's that. There's that. We found our antiderivative. Now, how do I know if that's correct? Yes, let's all take the derivative of that and make sure it's correct. Don't forget the product rule. Negative cos x, positive cos x disappear. The negative sine x times negative x is just x sine x. That's what I wanted to get to. I did it. I win. So this is correct. We just found the antiderivative of x sine x. Okay. Well, this brings us to an antiderivative that we don't know how to do yet. Actually, yeah, before we get there. The logical question is, how do I know what u and dv is? In the first problem, I said u was equal to, or the first time I attempted this, I said u is equal to x and dv was equal to sine x dx. Well, sometimes it's not going to be that easy with things being on the left side and on the right side. I could have picked u to be equal to sine x. So let's try this exact same antiderivative again, only with different u's and different dv's. Let's say u is sine x, and let's say dv is x dx. Well, this is the table that we would have to do every single time. So the table up here that we did for the previous problem, you will do this every single time you encounter a problem like this. It's a very crucial part. Selecting u, selecting dv, finding du, finding v. If I took the derivative of this u, I get cos x dx. If I take the antiderivative of dv, I get 1/2 x squared. Well, now I can rewrite this as not only just the antiderivative of x sine x, but as uv times the antiderivative of v du. So I get 1/2 x squared, that's v times u sine x, minus the antiderivative of v du. Dx. Well, what do we see here? If we choose the wrong u and dv, how do I know that's the wrong u and dv? I can't take the antiderivative of that v du. This I don't know how to do. Can't do this easily. Since I can't do this, I picked the wrong u dv. This is still correct. This is a correct correct rewritten antiderivative. This is correct. However, I still have an integral in it, so I'm not technically giving the correct antiderivative. Okay? So picking the correct u and dv is important. If you pick the wrong one, you'll get this that you can't figure out. All right, now that we know that, we're going to figure out the antiderivative of log x. And this will help us show that sometimes dv is just going to be the dx part. Now, you may think the antiderivative of log x dx is 1 over x, but that's not correct. That is the derivative of log x. So, don't make that mistake. Instead, we don't know what the antiderivative of log x. We never learned the rule for it, so we're going to discover it. We're going to use u dv. I'm going to say u is log x, and I'm going to say dv is just dx. Let's see what happens. Du is 1 over x. V, what is the antiderivative of dx? X. Okay, using the kind of equation, the rewritten product, of rewritten antiderivative of this product, we can say the antiderivative of log x dx is uv minus the antiderivative of v du. Well, we can see that this x and this 1 over x will cancel. I now have x log x minus the antiderivative of just dx. Well, that's x log x minus x. Plus a c, of course. Turns out this is the antiderivative of log x. A lot more complicated than you would have thought it was, considering the derivative is 1 over x. So let's find the antiderivative of x log x. Go ahead and give it a shot. See, most of you picked u as x and dv as log x, or log x dx. Well, using this u and this dv, this is rewritten as uv, so that's x times x log x minus x, minus the antiderivative of v du. Keep forgetting dx. Does that help us? No, because I have x log x. I can have it in the integral again. I couldn't find it in the first place. This doesn't help us. So let's go back. Let's start over. If that doesn't help us, what should we do instead? Pick a different u and pick a different dv. So Mr. Meyer, what do you think u should be instead of x? Yeah, it should just be the log x. And dv maybe is x and the dx. Let's see how that works out. Ms. Larea, we can have a quiz tomorrow if you really want. Do you really want? No, me neither. So let's just do this work and not be on our phones. I know. u v minus the antiderivative of v du. This helps me this time around because that x and that x can cancel, giving me just 1/2 x. Antiderivative of 1/2 x is 1/4 x squared. Plus a c. And we have just found the correct antiderivative for x log x. Seems crazy, seems messy, but that's what it is. That's the antiderivative of x log x. A lot more complicated than we thought it would be. But when we're going backwards, things get complicated. Guidelines for picking what u is. Always take logs first. So if you see ln x, pick ln x. That's typically your u. Next, your algebraic expressions, which really I don't like saying it's algebra, but it's x to a power, or just x. So log x pick first, x pick second. Typically, you won't even pick the t and the e. Sometimes you will. But at least for today, pick logs first, then pick x's second. Let's try one that you would have had to do for your homework. Check your answer with a neighbor. If we pick the correct u and dv, we have a new antiderivative over there on the right, which is just 1/5 x to the 4th dx. You take the antiderivative of that, you get 1/25 x to the 5th. You should do this one. All right, cool. We should have gotten x sine x plus cos x plus c. Fairly simple. Now, sometimes you have to do a repeated application of this procedure. This is what we saw on the movie. I said, you guys are going to have to learn how to do this. This is the last lesson. And they were doing it in the movie. I'm going to show you just the standard table method, or the standard way, picking u and dv, and then I'm going to show you a different way, which is considered the table method for u dv. Okay, using our kind of rules, what do we pick as u, Miss Lorea? No, that's the exponentials. That goes last. So instead of that, what do we pick? T squared. That means dv would be e to the t. Miss Lorea, what's the derivative of t squared? What would be du? Yep, 2t dt. Antiderivative of e to the t is just e to the t. Okay, well, we rewrite this as uv minus the antiderivative of v du. Well, what I see here is that this antiderivative I still can't take. Can't take e to the t times 2t. But I don't want to switch up my u and my dv, because if I did, it would be even more complex. What do I have to do? I have to actually do u dv again for this new antiderivative. I know. So what we have is this t squared e to the t minus a new u dv, which is uv minus the antiderivative of v du and now I have an antiderivative I can take. Antiderivative of 2e to the t is just 2e to the t. Distribute this negative, you get t squared e to the t minus 2t e to the t plus 2e to the t plus c. Turns out the derivative of that is just t squared e to the t. Or the antiderivative of t squared e to the t is that big mess. There is another way to do that that will take you less time if you ever encounter something like this in the future. And it's called the table method. So let's take this with us and let's make sure this answer is our answer. And here is the table method for getting this same answer. It is a helpful method for repeated application. It can be used other times. However, I feel like if you use logs in it, it doesn't work. I'd have to look into it. But we tried it with another class, it didn't work. Here's what you do. You start with your sign. Then you're going to have a U column and a DV column. It's all going to be columns. Your signs are going to alternate plus, minus, et cetera, et cetera. Whatever you would pick as your initial U, you'll pick for your U here. And then you are going to just continue to take the derivatives as you work downward. So the next spot, I'm going to say the derivative of t squared is 2t. The next spot, the derivative of 2t is 2. The next spot, the derivative of 2 is 0. Then over here on the dv side, you're going to use what you would have as dv. You don't have to include the dt. And what you're going to do on this column is you're going to take the antiderivatives. And you're going to keep going until you get to that last derivative, that 0. Okay, this is when the guy's freaking out. He's not getting the right answer. The dude shows up late. He says, go to the counselors. And then he says, tick, tack, toe. Simple. From the movie. All right, I'll show you. Don't worry. It all makes sense. See, he gets mad. He feels dumb. He wants to leave the class. Tic, tac, toe. Simple. That's what you just did. Okay? And see, what did he do wrong over here? Did he see it? What did he do wrong? He's trying to take the antiderivative of x squared sine x. What does he do? What did he do wrong? He's like, I can't do this. Well, yeah, duh, dude. Yeah, he picked u as sine x, and he picked dv as x squared. So he ends up with an integral of 1/3 x cubed cos x. Well, that doesn't help you out. So, dude, just flip-flop your u and your dv, and you're fine. Don't be so dramatic. All right. So if you use this table, now I like to do it this way, not the way he did it. You can see your answer. Positive t squared e to the t. Negative 2t e to the t. Positive 2 e to the t. Okay. See if I can find one more thing. Yeah. Yeah, don't use it with logs. It's really if you have x to a power and then either like cos or like a trig or e to the x, and you know you have to take the derivative of this x all the way down till it gets to 0, use the table. But for others, I would not use the table. Now, area under a curve using UDV. Okay, so this is now an area under a curve. But we know that to find areas under curves using the fundamental theorem of calculus, you just need to find the change in the antiderivative. Okay? Well, that means I need to find the antiderivative of x cos x. Well, to do this, I'd have to do UDV again. U is x, because that comes before the trig in the late mnemonic. That means du is equal to 1 and v is equal to sine x. Well, we got x sine x minus the antiderivative, but it's an integral, so it's going to be from 0 to pi over 2 of v du sine x. Well, I can write this as x sine x. This is going to be the change in negative cos x from 0 to pi over 2. So it must be x sine x. Cosine of pi over 2 is 0, so this is minus 0. Cosine of 0 is 1, so minus a negative 1. Does that make sense as an answer? X sine x minus 1. This is minus a negative 1. Yeah, why doesn't it make sense?
Because you didn't find the change in x sine x.
Exactly. This entire thing is the antiderivative. You have to find the change in both of them. So even when you write just u times v, right after you do that, you have to find the change in it too. Okay?
Not you don't include the minus 1 at the end.
You will include it. You will include the change in both of them.
But I mean, like, so the change in x sine x minus 1, or will be the change of x minus x, or x sine x minus 1 changes the x, the entire thing? From 0 to pi.
It's this, and I can write this, or you could have, what's the change in x sine x? Well, sine of pi over 2 is pi over 2, and then sine of 0 is 0. So it's either written out like this, so pi over 2 minus 1, or if you wanted to, you could write it as the antiderivative of x sine x plus cos x, that being the correct antiderivative, and find the change in that.
Gotcha.
You see what I'm saying?
Yeah,
Does
so
that
you don't do x sine x minus 1 and then change to that.
No, because we already found the change in negative cos x.
Gotcha.
That's where this came from.
All right.
Okay. So we get pi over 2 minus 1. Okay, this is very important. You have to find the change in the UV as well as the change in the VDU. UV as well as VDU. Okay, so let's do this one, then we'll finish up with one more problem. Find the area between, or the area under x squared log x from 1 to 2. Then use your calculator to check your answer. Remember what comes first? Logs first. Then the x squared. So u should be log x. UV minus VDU. Fingers crossed. Bless you. Remember, the log of 1 is 0. Questions? Not too bad. Just remember to take the change in both of your pieces. I like to do it in pieces. You could do it all at the end if you just found the antiderivative. You could have found the change in this entire thing. But I like to kind of keep them separate. And it helps to keep them separate when we do this next problem. In the future, one more thing. You might see a difficult antiderivative. You might want to use dv. Check U substitution first. And before you even check to do U substitution, try to simplify before that. Okay? In this problem, you might think UdV, but UdV actually makes things more complicated. If you just went back to simple U substitution, which you learned, U is equal to 1 over t, du is equal to negative 1 over t squared, dt. dt is equal to negative t squared du. This is a simple U substitution problem. Okay, so in the future, U substitution should come first. UdV comes second if U substitution fails or if simplification fails. All right, this is a question that was on a practice BC test because this is a BC topic, even though it should be an AB topic. So I figure you guys, after doing this lesson, can do this problem. So read the question, try to figure it out. I'll tell you right now, it's a UdV problem. So let's see if you can figure it out. Good. Good. UdV, U is x, dv is f prime. If you didn't do that yet, try that now. Not that bad. Okay, just UDV. There's other problems just like this. This is a good problem. Here's another problem. Here we have the antiderivative of f of x sine x. We say that's equal to negative f of x cos x plus the integral of 4x cubed cos x. Which of the following could be f of x? Well, you got to figure this is uv minus v du. Well, if v is repeated, that's got to be v. So that means u has got to be f of x, and this has to be du 4x cubed. Well, if du is 4x cubed, u has got to be x to the fourth. But the question is it the negative x to the fourth or the positive x to the fourth? Well, dv is sine x. V would be negative cos x. Negative cos x, this should be minus this. It ends up being the positive x to the fourth. All right. That's UDV. I hope you keep that in your brains for future calculus classes.